Dr. Wang from Pittsburgh Supercomputing Center. He will talk about the hand-on tutorial on how to do the calculation of what Marcus just talked about. Go ahead. Yeah.
Okay. So I'll start. Thank you everyone for coming to this presentation. So today I'm going to give a short tutorial on how to use must. So I'm going to introduce this particular package and tell you how this can be done and what's usefulness of this. Okay, so I'm going to give you some examples of doing this and what kind of physical result you can get out of this package. So this is a project supported by a National Science Foundation. We have multiple participants. It's an international collaboration effort. So what is must really? It's an interesting word, of course. It's made out of its combination of it stands for multiple scattering theory. We pick up the first two characters from multiple, and then S scattering, T and theory. So multiple scattering theory, as Marcus has briefly explained in his talk. So multiple scattering theory is a method for solving the Kong-Shan equation, which is the one electron Schrödinger equation that governs the electronic structure of solids. So as Marcus explained, that in the original problem was like given a material will have many electron system, right? But by applying the density function theory, we can convert the problem into one electron problem. The equation you get is become a one electron Schrödinger equation. Normally we call it a different name called the Kong-Shan equation, but it's just a one electron Schrödinger equation, which governs the electronic behavior in solids. So this particular method, multiple scattering theory, utilizes the so-called Green's function of the Kong-Shan equation. So instead of solving the differential equation, which is Kong-Shan equation, but we just calculate Green's function, and then because the central quantity of the density function theory is the density. The Green's function gives you a very convenient way to calculate density. By just taking the imaginary part of the Green's function, you get density. So that's kind of a different approach to the Kong-Shan equation. So must is a computational tool for so-called ab initio electronic structure calculations. So as you read the literatures, people talk about ab initio. So-called ab initio really means that the electronic structure is determined based on the fundamental physical law, which in this case is quantum mechanics rather than on the empirical models with adjustable parameters. There are other popular ab initio packages besides must, such as VASP, Yin2K, ELK, Abinit, Quantum Espresso, etc. And they're all based on different approaches, but they all try to solve the Kong-Shan equation. But must is based on multiple scattering theory. It tries to calculate the Green's function. Okay, there are kind of major difference is there, and so that's just different approach to it. For this must project, we already set up a YouTube channel for people to watch. That like for today's course, we're going to upload onto YouTube, so you can always watch, kind of review it, and sometime in the down in the future, you can always watch it. So it's going to keep on the YouTube, and also that channel includes our other seminars and other online lectures and tutorials. Also you can find on that channel. So welcome to visit this channel, and welcome to subscribe to this channel. So how do we obtain must? This package is open source. Easy to obtain it. It's on GitHub. So all you have to do is on your computer, laptop, or whatever, a terminal connected with a large cluster. Again, all you have to type the command git with clone and typing this website with web link. Then what happens is once you do that, the package will be downloaded onto your local computer, and there will be a must directory will be created on the local space. Okay, on the must, you're going to see a lot of subdirectories in the files all in there. So once you do this step, you got the package. of course, you have to install it, compile it, you have to build executables. The basic fundamental requirement is you have a Linux system, including Mac OS X, or if you have a Windows, you can always install Windows. It's called subsystem for Linux. If you're not familiar with it, you can go to Microsoft Store. You can find Microsoft Windows subsystem for Linux. You can just install it, and then you will have Linux running on your under your Windows system. Okay, so then you have to have compilers, Fortran, C, and C++. For example, you can use GCC, which includes both C, C++, and the Fortran, Fortran. Okay, and also you need MPI message library. For example, OpenMPI. This is all free to download. It's freely available. There's a few other freely available MPI library packages you can always try to use. Once you have that, those very fundamental packages you need. Once you have that, you will be able to build a must package on your computer. And there's a installation steps describing this installation file. You can take a look at that. Follow the steps. It's quite easy. Generally, you can once you do that, you can just build and then have an executable available for you to use. So for further information, you can also visit this particular website. This wiki page for this project must, and it tells you about this project and also tell you how to install and build your this must package on your computer. Okay, now what's the usefulness? How do we use it? Right. So let's take a simple example. Copper zinc as an example. It's an alloy, right? So copper zinc is known as brass. Right? It's a very ancient, and people have used this for thousands of years. You can see all this these things displayed in museums, and this obviously human civilization have been using brass for long time. Brass has long been popular material for decoration for its bright gold-like appearance. Example for drawer pulls and doorknobs, and has also been widely used for all sorts of utensils due to many properties such as low melting point, which is high workability, durability, electrical and thermal conductivity. And at zero temperature, T equals 0, copper zinc exists as ordered intermetallic compound in B2 structure. And I'm going to show you what B2 structure look like. It's an ordered structure. Okay, copper and the zinc atoms are arranged in an ordered manner in copper zinc alloy at zero temperature. So basically, it just looks like this. So you see, if you look at a little cube, like all the corners are occupied by one particular type atom. Like for example, we can call copper. The center one is occupied by zinc. So this, so obviously, it's a kind of ordered structure. It's called a B2 structure. So it's for low temperature, copper zinc will exist in this particular format. When increased temperature above 730 Kelvin degree, the materials become a random alloy. That is, on atomic site, the copper and zinc are randomly distributed. It's no longer become this ordered structure. Okay, so this order disorder phase transition take place, so that this color could be either copper or zinc, which is kind of randomly. So I just use this particular color to represent this kind of randomness of a particular. It's a kind of random, given any particular site. Could be copper, could be zinc, depending on the concentration. So this is called A2 structure, or BCC structure, no matter which way you call it. Okay, so this is kind of give you some kind of background of the particular physical system we are going to deal with. Right, this is a kind of alloy that it could become random as temperature increases. So how are we going to use must to deal with this type of problem? So we have like on the must package, if you download it, there's a directory called tutorials, and there's a particular example called copper zinc that shows give you an example that how do we calculate copper zinc. Okay, so how do we deal with copper zinc? Well, so what we do here is we have three different structures to look at copper zinc alloy. One is called P2 structure. Basically, just try to calculate if copper zinc arrange this ordered structure, how we're going to use must package to calculate the energy of that system. And one of the variables is called lattice constant. That is the size of the unit cell. That tell you how far away the atoms are in the volume or the alloy. Basically, just this is called the lattice constant. Another structure is called PCC, means that the atoms are randomly arranged on underlying lattice. Okay, it's called PCC structure, the lattice constant, and each side could be copper, could be zinc, is randomly distributed. We know that because at high temperature, it's a random alloy. So how do we simulate random alloys? For low temperature, it's easy. We know it's ordered, right? It's easy to do. But for high temperature, when we simulate random alloy, we can use this type of particular approach, so-called the coherent potential approximation. That is, we try to find the effective medium that represents such a system. Okay, that's one way of doing that. Another way for doing it is to set up a large unit cell. So that large unit cell contains many atoms. The atoms are randomly distributed on the underlying lattice. But we use large unit cell to mimic the random alloy. That's another approach called supercell, a large unit or supercell approach. So it's basically described by this particular example. So we take three different particular examples to study copper zinc for different structures. One is called the B2 structure. We know at low temperature exists this way, or at high temperature it becomes random alloy. There's two ways to approach to the random alloys. One way is based on coherent potential approximation. Look at this particular structure, or we use large unit cell to simulate the random structure. Okay, so that in that large unit cell, the atoms are randomly distributed. Okay, so this is basically the structure try to do. This is what it's trying to do. All right, so we have three different examples that we use must to run the calculation. Okay, now let me let's use a particular calculation as an example. So the input data for run the simulation, it's all can be found under this. Right? So the executable is called MST2, which can be found under must/bin, or you can find also must_MST_bin. This are the same. They're because there's a symbolic link to it. So they are just you found the same file on both directly, but they're actually the same thing. All right. So this is the executable we're going to use to run the calculation. So basically, when you run the calculation, we need three type of input data for doing that. One is called description data, which controls some parameters, controls how you're going to run this code. So basically tell you how many iterations you're going to run the calculation. Some other parameters which controls k points, or where to find the position data. What's the potential files? What's the name of potential file? Basically, this is kind of controlling this description data. It's stored in. You can call it whatever you like. I just happen to call I_new, but you can call it whatever you want. Okay. And the system structure data, I call position.data. The file name can be arbitrary. You can call it whatever you like, but it has to be consistent with whatever given in this description data. Okay, now I call position data that contains that position of the atoms in the system that you try to simulate. And then, of course, when you run calculation, you have to have some kind of starting potential, where in this case, we only have copper and zinc. So we have starting potential for copper atom and starting potential for zinc atom. Okay, so this is a kind of starting potential to begin with, to start the calculation. Okay, so these are basically three types of input data required to run the calculation. Now, to run the calculation, what you have to do is you do MPI run. If you're not familiar with it, this is a executable building to this called MPI library. Basically, what happens is it starts many MPI processes that it runs this executable on multiple processes. They all could talk to one another. So that allows you to parallelize your calculations. So this is just a fundamental kind of a command to start the process. minus NP is a kind of option that it tells how many CPU cores you're going to use for run calculation. The more cores you use, of course, it will be highly parallelized, and the less time you're gonna use to run the calculation. So this is the real executable you try to run. Okay, so MS2 is the one that's the executable you're going to use to run this calculation. And this arrow means that I'm going to take this file as input. So my file name happens to be called I_new, but you can call whatever you like. Okay, so this basically what you have to make sure that this file name is the discrete data file name, right? So basically, it's just called command to run this calculation. Okay, so in your real calculation, you just specify to give whatever the number actual CPU core you want to use. So just basically put that number here, right? To run this, you can, for the B2 structure, we use KKR method to run the calculation. KKR method is designed to run with all of the structures. Okay, and for the BCC, because we use a coherent potential approximation, with the method we run is called KKR CPA method. Which method you use is all controlled by it's all described by the I_new. I'm going to show you the particular example, right? So for the supercell calculation, you're going to use the LSU method because it's a linear scaling. Because when you have a large unit cell, it's more convenient, it's more economical to run with the LSU method. It's a linear scaling method. Okay, it takes less time to run the calculation. In this particular example, I use a 16-atom supercell. Okay, with 8 copper and 8 zinc, which is placed randomly in the supercell. Try to mimic the random alloy. But in reality, for real simulation, we try to use a larger unit cell to try to mimic the random alloy, right? The larger the better. So in this case, just small tutorial. So I only put like a 16-atom supercell, all right? But in the real world case, we use hundreds of or even thousands of atoms unit cell, right? So LSU becomes really important tool to use because it's a linear scaling. If you use KKR to do that, of course you can use KKR, but it takes much longer to run calculation. The community cost is much heavy for using KKR for this type of supercell. Okay. All right. So let's use this one particular example I give you is now. Let's look at this random structure for BCC structure. We use the KKR CPA method. All right. So let's do that particular example. So let's just go to this particular subdirectory. And discrete data is given this by this, right? So this is just I take piece out and show you how this look like. Now the first question is how many atoms in the system? Only one, because it's a CP. I try to use a effective medium that each effective medium atom it's not real. It's kind of average copper and zinc. Okay, it's kind of average of copper zinc. So that average effective atom occupies each atomic site. Okay, so that's only one atom per unit cell, okay, because that repeats itself over the entire crystal. So there's only one type, one atom. This kind of effective atom is one. Position data is given by this name. All right. The starting potential is copper and zinc, which is provided. The method I'm going to choose is number 3 is it means a KKR CPA method, and the few other parameters you control determines how you're going to do the cutoff for the angular momentums and the k-space integration parameters. All this in setting in this description data. So this one particularly means that I'm going to have only one particular site, and so the each meaningful line that it's contains the double column means that on the left side is a description, on the right hand side is a kind of value of that description. Any lines without this, it means just comments. It's just treated as comments. It's not going to just ignored by the program. Okay. All right. So how the particular data look like? This particular data look like that. This basically this 3 lines shows the unit cell. Then this first line shows that there's a scaling factor. Basically, it just tells you what's a lattice parameter, lattice constant. Okay, so this number will be applied to all these numbers, So basically tell you the dimension, the size of the unit cell. And because you have only one atom per unit cell, in this case, because we are doing KKR CPA, so each side is occupied by called CPA medium. So the atom type is called CPA, which means contains 50% of possible of copper, 50% of zinc. Of course, you can change the parameter. You can change, say you have 80% copper and 20% zinc. It's all possible. So, but you run your calculation depending on what kind of alloy you're going to simulate. In this case, particular example, my copper is 50%, zinc is 50%. Okay, so this 0.5 represents the concentration of each chemical species. Okay, once I have that, I run. Another thing I have to remember that this number I'm using like in atomic units. So this number is in the Bohr radius. Bohr radii, one unit of Bohr radii is 0.529 angstrom. Okay, so I'm using Bohr radii as atomic units. So this number is atomic unit, atomic units. Okay. Again, the line starting with pound sign is treated as common. So, okay, so copper and CPA. That's already explained that. Here's how you run it. Okay, you go to this directory. I'm going to use 16 CPU cores to run this calculation. So this is how I do it, right? And once it's going to run like for 100 seconds, something also, then go to finish. Quite fast. So if you can pick up one of the output data is called a K file. It's a simple description of the result. You can take a look at this file. Okay, so here's an example how it looks like. That this is a copper zinc random alloy in BCC structure. There's only one atom type. One really means it's a CPU, it's a CPA medium. So just don't confuse it. This is a CPA medium. Actually, this includes possible two type of atoms. So it finishes in 17 iterations. So it finished the calculation. And the total energy, the binary energy is in atomic units. So total energy is in the Rydberg. So one Rydberg is 13.6 electron volts. So the total energy turns out to be this number plus this number. So it's a negative 3414.462692 Rydberg. That's the energy per atom of this random alloy. Okay. All right. So you run this calculation. This is for particular given lattice constant. Then you can change the lattice constant in the position data. Change the lattice constant. You run this calculation for different lattice constant. You get different energies. Then you can make a plot. Okay, so you can plot the energy versus the lattice constant. Okay, so this is the lattice constant. It changes the size. What happens is you get such a very beautiful parabolic curve. Okay, so on the left-hand side is just this y-axis shows the total energy value. Remember, this is plus 3414. Okay, I don't want to have like a lot of digits on my plot. So this is just a way of presenting the data. So on the x-axis, it is a lattice constant in atomic units. Okay, so you see this parabolic curve that you see there's one particular lattice constant. The energy is minimum. This is called equilibrium lattice constant. That's the lattice constant that the alloy will exist at this particular lattice constant, because here it gives the minimal energy. And another interesting thing is when you increase the lattice constant, it means that you stretch the material, or you decrease the lattice constant means that you compress the material. The energy will increase. Okay, so the energy, if it increases quickly, means that the material is a harder material. If the material the energy increases slowly, means that it's a kind of soft material. So it's going easily you can correlate that to the actual physical reality. Okay, so what we can learn from this? The equilibrium lattice crystal structure at t equal to 0, because all this calculation is done at t equal to 0. Okay, so this is a number we get. All right, so it shows you what's the equilibrium lattice crystal structure. The lattice constant value is this number. All right, so that's the equilibrium lattice constant is this value. It's 5.53. Okay, mechanical property of the alloy shows that depend on based on the energy versus the lattice constant, shows you how the whether the material is hard material or soft material, right? If you find the energy increase quickly, it means that it's a hard material. Otherwise, it will be a soft material. Right? So basically, it can give you some information about the mechanical properties of this. All right. So we can run the same calculation for B2 structure. Okay. Basically, in the input data, what you have to do is to choose this 2, which means the previous calculation I used 3 means KKR CPA. But for this structure, it's a KKR method. I just choose to be 2, right? So the position data now is because it's an ordered structure. I have 2 atom pin in the cell, right? It's ordered structure. One at the corner is copper, and the corner center is zinc. Okay, it's a unit cell. It repeats to forming a crystal in the entire space. So this is a lattice constant. So you can run this calculation. All right. So 2 atoms here corresponding to these 2 atoms here. Okay. Again, atomic units is this atomic unit. We use atomic units for the lattice constant. And here you run the calculation exact same way. Okay, same executable. I use 16 cores, and then you check the result by doing this, right? Or you can do unit cell, a large unit cell calculation using usefulness method. Okay, look at the input data. Now I choose option 1 means usefulness, large unit cells. For large unit cell, because large unit cell, the position data become large, right? You have 16 atoms in it. Okay, there's 16 atoms here, where copper zinc are arranged actually randomly on the underlying lattice. There's a lattice constant, and the 16 atoms, 8 is copper and 8 is zinc. So this 16 and corresponding to this atom 16, right? And there's another parameter actually for the running LSMS. It's called the local interaction zone size. That's a kind of cutoff radius. It's a kind of controlling parameter you can use. Okay, anyhow, so given 4 core run, you can run this job with reduced computing time. Okay, so actually I ran that with 16 cores, whatever you can do. No matter how many cores you're going to try to use, how available to you, you can run. The more cores you use, generally you use less time to run the calculation. Okay, anyway, so how we compare these 3 different calculations, all right? Of course, for the B2 structure, this is we use KKR calculation, KKR method, we get this number like this, all right? For BCC structure, it's for real random alloy, all right? This B2 is an ordered alloy, ordered structure. For BCC, we assume that's a random alloy. Okay, copper and zinc are randomly distributed on the underlying lattice. So we do the KKR CPA calculation. This is the total energy we got. On the other hand, another disordered structure is we use a supercell that we put copper zinc randomly in the unit cell, and then we run arithmetic calculations, and this is the total energy we got. How do they compare with one another? Remember, we do the calculating all T temperature equal to 0, right? So obviously, well, with the same lattice constant, by the way. Okay. Now let's take a look the comparison of the total energy. They are very close to one another, isn't it? But there's some differences in the millirubric, and it turns out B2 structure has low energy. Okay. Remember, this is a negative sign. Okay. So this has the lowest energy among all 3 different structures. And so it turns out, so obviously at T equals 0, copper zinc prefer to be this structure because it has lower energy, which agree with the experiment. As I told you at the beginning, that at lowest temperature, the alloy tend to form an ordered structure. And by reality, in our calculation, it is turned out to be true. That agrees with the experiment that ordered structure does have low energy, in this case, for copper zinc. All right. So another thing is you may consider what's the energy difference between this this ordered structure and random structure, because this represents a random structure. The energy difference is about 5.8 millirubric, and in EV is 0.0789 EVs, electron volts, right? So we can estimate the transition temperature or the disordered transition temperature, because this means order, this disorder, right? You can make a very naive estimate what's the transient temperature based on energy difference. That is using this very simple formula. TC is, you can do these simple calculations that it turns out to be 946.6 Kelvin. You can compare with experiment. It turns out experiment is 730 Kelvin. We know this such estimate is usually overestimate, but it's kind of in an interesting comparison you can make. All right. So that's, I just want to share how must can be used, and it's a very simple example. You can I just show how you can try, and you're welcome to download the code, install it, and on your own, and try to practice on your own, and pick up some other alloy system. Doesn't have to call zinc, and do your own, and have a good feeling of it, and try to explain compare with the experiment. Okay, so all this is done on computer, right? So you can imagine that it's called alloy design, that without doing the experiment to make the alloy, you can do that on computer. To design a computer by changing the compositions to see what's the mechanical properties, what's whether there's energy, how low the energy could be, whether it can form a structure, which structure has low energy, what kind of phase will exist. So all these things can be done on computer. Right? Okay, that's all my talk, and I would welcome questions.
Thank you, Jan. So I already see someone want to ask question. Go ahead if you want. Anyone want to ask question?
Yeah, hello.
Yes.
Yeah, I was just gonna ask about when you use the CPA method versus a supercell method. For example, is the concentration that you approximate for the CPA method the same as the one you get for the unit cells?
That's right. When you compare CPA method and the supercell method, when you make the comparison, of course, you have to make sure that the concentration have to be the same. All right. Otherwise, this comparison will make no sense. But so that will have a problem, because for CPA, the concentration can be any arbitrary number. Okay, you can adjust it any way you want. But for supercell, since the supercell you have finite number of atoms in it, the concentration can be tricky, right? Sometimes it's not going to apply unless you use a very large number of large unit cell, has a lot of atoms in it. You can find concentration corresponding to the one what you want.
So there are basically advantages and disadvantages to using both methods. So for one thing, as Yang pointed out, in CPA, you can use any arbitrary concentration very easily, but as the name says, it's a coherent potential approximation. It is a mean field approximation to the disorder in the system. So in supercell calculation, you actually account for the longer range effects of the disorder much more readily, and you can also incorporate more easily local correlations. So if you have, if you construct your supercell accounting for slight differences in the probability of finding some type of atom next to different type of atom.
Yeah, that's a very good point. That for the supercell calculation with the Earth mass, you can take into account the Schrodinger correlation effect, Schrodinger order. That's the jargon terminology we use. While for CPA, for this simple conventional KKR CPA, you assume that there's no correlation between chemical species. For any given species, it doesn't matter which it tend to be like to be neighbored by different type or same type. It doesn't matter. It's no short-range chemical correlation in it.
Okay, thank you. Appreciate it.
Any more questions?
Yeah, I had a question.
Go ahead.
Okay.
So whenever you would actually go to measure something like this, I think you call it like an equilibrium lattice constant or something
Yes.
like that. So by changing that lattice constant, you're going to be changing the bond enthalpy, right, or something, and then that'll have some effect on the chemistry or some other macroscopic property.
You can use the in chemist language that you call the bond length. You
Yes.
actually change the bond length.
Yes.
Yes, you change the correlation also.
I see. So then down here where you're approximating this this transition temperature, are you trying to say that like this energy is the Gibbs free energy or like the Helmholtz free energy?
Yeah, okay. This estimate is a very naive way of estimating it. There's no entropy in it.
This just really compares the enthalpy. So
Okay.
there is, and that is why actually, as Yang said, usually this estimation is higher. And one important factor is this just energy comparison completely ignores the entropy effects.
Yeah. I just said this is a very naive way of doing it. It's a back in the envelope calculation.
So if you have a big computer, you can actually combine a supercell calculation with Monte Carlo simulation, where you sample many different realizations of the random disorder in the cell and calculate the actual finite temperature statistical physics. And we've done that some years ago for copper, zinc, and then we'll get actually very good agreement with experimental value. But that requires a big supercomputer and lots of computer time.
I can imagine. So how would you incorporate just calculating that change in entropy then? You'd have to start, I don't even think. You have to try and start thinking of like random orientations of all of these.
So what you use is a method called Metropolis Monte Carlo. Basically, you you weight these samples based on the Boltzmann factor of their according to their energy.
Yeah, the calculating entropy is difficult, but simulation basically allow you not to avoid calculating entropy. They're not simulation. Okay.
That's very interesting. Thank you.
Any other questions?
What's like a reliable method to like deal with like temperature dependence of disorder?
Okay. Yeah, temperature dependence of disorder. That's right. Like for example, you can use a Monte Carlo simulation technique. Then because for CPA can only give you like an energy component. Right?
Yeah, so would there be like some kind of outer loop where you're like updating the, I guess, the ratio or something? Oh, wow.
Correct, yeah.
Okay, thanks.
At most, we can do is we can introduce temperature to the electronic temperature. That's the best thing we can do for in the KKR CPA for electronic temperature. But we still don't have there's no capability for us to introduce temperature for this iron, the atom there. There's no way we can do the temperature. But
so to account basically for the entropy, you will have to really do some type of supercell calculation, and because doing it really using this density functional theory is very expensive. What one normally does is you perform calculations for a number of representative supercells using density functional theory, and then fit this to an easy model that is much faster to evaluate, nowadays using machine learning for that, for example, and then use that within the Monte Carlo simulation to account for the entropy. So it's a multi-step process, but again, it gets very good, can get you very good understanding on what happens in these in these alloys. Right now, it's the system that Yang presented is a very easy one in a sense. It's just two components, and it's either ordered or disordered. Imagine you mix more than two elements, and what then can happen, it actually can also separate into different phases where you have where you then have two regions with different composition in your material.
All right, thank you.
Any more questions? If not, thank you, Marcus and Jan, one more time. And thanks everyone for joining the tutorial. Thank you.
Okay, thank you. Bye-bye.
See you guys next time.